Okay, welcome back to Algebra 2 Semester 1 Final Review. This time we're going to be looking at models for problems 15, 16, and 17. The first one here is an absolute value with an equation. You can see that there's an equal sign here. And what we're going to be doing here is splitting this problem up into two separate problems. Either 2x plus 7 equals 5, or, and you make another copy just like that one, and on this right-hand side over here, you make one more change. You multiply the left-hand side by -1. Now, what that effectively does is you're basically multiplying this inside part right here by -1, and that'll change the sign, but the absolute value counteracts that, so this is how you get your second answer here, by multiplying the second copy by -1 like this. So let's solve the first example here. You subtract 7 from both sides. When you subtract 7 from 5, you get -2. And then dividing by 2 here, you get x equals -1. All right, on the other one, what we're going to get here is when you distribute -2x minus 7 equals 5. Adding 7 to both sides gets us to 12, and then dividing by -2 gives an answer of -6. Okay, it tells us that we have to check for extraneous roots. What that means is we have to just check these answers and see if they work. So we're going to do this -1 to start with. 2 times -1, that's -2, plus 7 would be 5. The absolute value of 5 actually equals 5, so that one works. When you put -6 in for x, that's our second answer. We're going to check that. 2 times -6 would be -12. Adding 7 gives -5, and the absolute value of -5 also equals 5. So this is a case where neither of the answers is extraneous. They both work. Okay, an absolute value inequality. There's two types here. First, you have to get the absolute value part by itself. So you can't distribute that 3. You have to divide by 3. Okay, when you get down to this stage, if you've got a greater than sign, you're going to use or when you split it up. And I'll remind you that greater than would be spelled ER, but I spelled it OR to remind you that greater than right here goes with the OR split. I know I misspelled greater, but that's to remind you that it's OR. Okay, x plus 4 is greater than 5, or x plus 4, we make a second copy over there, and you'll notice that I'm leaving the absolute value bars off this time. Multiply this side by -1, and we're off to the races. We know by subtracting 4 from both sides that x has to be greater than 1, or this will be a little more complicated. Add 4 to both sides and divide by -1, which tells us that x is less than -9. You'll notice I hope that I switched the direction of the inequality. Okay, now we're going to graph this thing, so let me get a number line going here. And I got to get the numbers 1 and -9 going here, so I'll put 0 up a little bit to the right. Okay, we need to be bigger than 1 or less than -9. And there's the graphical version of the solution set. Okay, we got one more example like this. And once again, you have to isolate the absolute value bars. So since you can't distribute, you have to divide here. And that changes the direction of the inequality. So now we have a less than sign. And the mnemonic device that reminds you of the next step is it's less than. Normally I would spell it like that, but instead I'm going to remind you that you use the word and by adding the extra letter there and using caps, less than. So we need an and statement anytime you have a less than symbol at this stage. X plus 3 is less than 4, which tells us x is less than 1. And then on the other one, x plus 3 is less than 4. We multiply this left-hand side by negative 1, distribute. Add 3 to both sides. Divide by negative 1, which changes the direction of the inequality. So we need numbers that are less than 1 and greater than negative 7. And these type have to be combined into an in-between statement. We need to shade the numbers that are in between 1 and, in between negative 7. Smaller number goes on the left on positive 1. So the graph is going to be all the numbers in between those values. So I'll put 0 there. 1, 2, 3, 4. There's negative 5. The numbers in between negative 7 and positive 1 are the ones that work in this graph. Now, if the original problem had a greater than or equal to instead of just a greater than sign, I would be shading those two dots solid. So these are the models for 15, 16.